Right, and now I'm going to talk to you about reversible reactions and energy changes. So if you remember, the reversible reaction that we were looking at is our blue copper 2-sulfate crystals that are hydrated. They have water associated with their crystals. If you heat those, then you form anhydrous copper 2-sulfate crystals that are white and 5 water molecules. So in terms of energy changes, from the last unit, you'll remember that an endothermic reaction is a reaction that takes an energy from the surroundings, takes in energy from the surroundings. And an exothermic reaction is a reaction that gives out energy to the surroundings. So in terms of an energy profile diagram, if we look at an energy profile diagram for an endothermic reaction, we can label the axes as the progress of the reaction. So the x-axis is the progress of the reaction and the y-axis is for energy. And in an endothermic reaction, we take our reactants, which is our hydrated copper 2-sulfate. So if we take our hydrated copper 2-sulfate and we put that in on our energy profile diagram, then we can put that down here. And then if we take our products, which is our anhydrous copper 2-sulfate and 5 water molecules. So we've got our anhydrous copper sulfate and our 5 water molecules. We can draw an energy profile like that. So if we start drawing arrows into that, we can draw a straight arrow from the energy of the reactants to the peak of the curve here. So that there is our activation energy. That's the minimum energy required for the reaction to start. And then we can draw an arrow here to show that, and this arrow here shows that 78 kilojoules per mole, so 78 kilojoules of energy per mole of substance is given. So energy is taken in from the surroundings. So the products have more energy than the reactants because energy has been taken in. So we do use a plus sign to show that this is an endothermic reaction, and the value for that reaction is plus 78 kilojoules per mole. However, if one reaction is endothermic in a reversible reaction, the reaction in the opposite direction is exothermic. So if the reaction here in the forward direction is endothermic, then we will apply our knowledge and we know that our reaction in the opposite direction is exothermic. So the forward reaction is endothermic, the backward reaction is exothermic. So to look at an exothermic reaction profile, and we've got the same, we've got our progress of the reaction and we've got our energy. Now, in an exothermic reaction, energy is given out to the surroundings. So in this particular example here, our reactants for the backward reaction have more enthalpy than our products, which will be the hydrated copper 2-sulfate crystals. So if we look at the energy profile here, we can see our activation energy is here, the minimum energy required for the reaction to take place, and then the energy change for the reaction is this arrow here, like this. So if we look at just the energy change overall for the reaction, we can see that energy is given out to the surroundings. The products have less energy than the reactants. And the value for this arrow, so in the forward direction, remember we said that the reaction was endothermic and we had a value of plus 78 kilojoules per mole. So here, 78 kilojoules per mole of energy is taken in from the surroundings. So in this reverse reaction here, if that is exothermic, the value is going to be exactly the same. 78 kilojoules per mole of energy is given out to the surroundings, and this is an exothermic reaction. So I can show that on my arrow here. The negative is because it's an exothermic reaction. 78 kilojoules per mole of energy is given out to the surroundings in an exothermic reaction, and 78 kilojoules per mole of energy is taken in from the surroundings in an endothermic reaction.